Welcome to the course of Advanced Classical Mechanics. My name is Mikhail Frolov, and today we're going to talk about Lagrangian equation of second time. But before that, we're going to talk about generalized coordinates. So we are going to talk about the meaning of generalized coordinates. So what is generalized coordinates? So let's say we have n particles, and n particles we can describe in terms of vectors, n vectors, and each vector has three Cartesian coordinates. Moreover, for that system, we have n constraints, and that constraints, we assume that constraints are holonomic. So in general, we have k equations right here, nonlinear equations, and in order to solve that system, so we can express k coordinates through the 3n minus k coordinates. In other words, so let's say that we express x1 in terms of xk plus 1 up to x3n, and of course that maybe depends on time. And up to k coordinates, we can do similar things. So in other words, so we have k dependent variables and 3n minus k independent variables. So if we have 3n minus k independent variables, in that situation, we can say that our mechanical system has a 3n minus k degrees of freedom. So we have 3n minus k parameters, and by using that 3n minus k parameters, we can completely describe our system. So in general case, if we can introduce some set of independent variables which can completely describe dynamics of our system, so that variables we call generalized coordinates. So let me give you some small examples. So let's say we have a particle in three-dimensional, and position of this particle we can describe by three parameters, let's say Cartesian coordinates. But instead of Cartesian coordinates, so we can introduce spherical coordinates. We can introduce angle theta, we can introduce distance from origin to that point, and we can introduce angle phi. So if our particle moves on the surface, let's say surface of the sphere, so the distance between origin and our particle will keep in a constant. So in that case, so we need only two parameters, two angles, theta and phi, to describe our system. So in that case, we call that our system has 2 degrees of freedom. So let's say that we have a system when our particle moves along a cone, and the distance between origin of that cone and our particle keeps as a constant. In that case, we need only one parameter, phi, and for that case, we have a system with 1 degree of freedom. So let's move to another example. So we have a bar on the ramp, and how many degrees of freedom we have in that situation? For that situation, we have only 1 degree of freedom, and we can choose any one parameter to describe the dynamics of this system. So, for instance, so we can choose x coordinate, or we can choose y coordinates, or we can choose the distance between origin of this ramp and that bar. So all the three parameters are completely equivalent, and we need only one parameter to describe our system. So why? So because we have a constraint, and that constraint connects y and x coordinate. So if we have L is the distance between origin of our ramp up to our bar. So also by using that two formulas, we can connect x and y coordinates. So L, in that case, is a generalized coordinate. So let's consider an Atwood machine. So we have two bars with a mass m1 and m2. And we have an unstretchable line which connects these two bars. So how many degrees of freedom we have here? So for first side, so that system should have 2 degrees of freedom because we have two bars. But that's another case, because we have an unstretchable line here. So is the line unstretchable? The distance, or all that line from that guy to that guy, so it's a constant. So if we introduce coordinate of first bar, coordinates of second bar, y2, and we introduce the length of the green line here, so the sum of these three guys are constant. So in here, we have to choose only one parameter, y1 or y2, to describe that system. So if we found, let's say, y1, so by using that constraint, L equals y1 plus y2 plus pi multiplied by a is the radius of this circle, we can find second coordinates. So let's consider more advanced example. So we have a spiral here with a constant step h, and now we have a particle which moves along of the spiral. So how many degrees of freedom we have for that situation? 3, 2, or 1? So the answer is 1. So let's look on that system from the bottom. So if you look from the bottom, so we see that particle will move along of circle with a radius of a. So this, to describe motion along of this cycle, we need only one parameter, a, because the distance between origin of this cycle to the spiral is a constant and equals a. So, but how about z-axis? Because we have a motion in 3 dimensions. So z also connects with the phi. So h is a step, 2 pi is a full circle. So if we have a full circle, so if we change phi from 0 to 2 pi, so we will make a step equals h. But here we have some note. Phi is usually changes from 0 to 2 pi. But in that example, so we extended our changing of our phi from minus infinity to plus infinity. So that is some small introduction to the generalized coordinates, and we will use generalized coordinates for the next lecture, where we will discuss Lagrange equation of second type.